All right. Somebody asked me about one of these circular motion problems, the one with the golf cart, number 4. So let me go over that one, and then um, I could probably take another homework question after that if people have them, and then we'll go on to the new topic. Um, okay, so circular motion. Number 4. So it's a golf cart. That's how you know it's a golf cart. Um, it has wheels with a radius of 0.15. Well, let me draw a little better circle for the wheel we're going to use. And okay, so the radius is 0.15 meters. It rolls along a flat ground. The wheels rotate counterclockwise at 8 radians per second. Okay, I guess it's going in reverse. So counterclockwise at 8 radians per second. Can everyone visualize how that direction of rotation means the cart is going backwards? I mean, it doesn't have to be going backwards. Just the way I drew it, it has to be going backwards. If I'd drawn it the other way around, it would be forwards. And it's accelerating clockwise at 12 radians per second squared. So what direction is the golf cart moving? Is it speeding up or slowing down? What's the velocity vector of the golf cart? What's the acceleration vector of the golf cart? So the direction it's moving has to do with velocities. Okay, and so from the angular velocity of the wheels rotating that way, it has to be moving this way. Okay, so we know that the velocity of the golf cart is this way. And if you have a angular acceleration clockwise, that means the acceleration has to be that way. Is it speeding up or slowing down? It's slowing down because the angular velocity and angular acceleration are in opposite directions. The velocity vector. So now we're going to get into the rolling without slipping equations. So if we have a coordinate system with the y-axis pointing out of the surface, then for rolling without slipping, the velocity vector of the center of the wheel, and the center of the wheel is moving rigidly with the golf cart, so this is also the velocity of the body of the vehicle, is equal to, in the x direction, negative omega r, and 0 in the y direction. And so we have negative. Is omega positive or negative 8? Positive because it's counterclockwise. And r is 0.15 meters. And then 0 in the y direction. So the velocity is negative 1.2. Zero. Or if you want to visualize that, it's in the negative x direction. So you can think of that as a velocity in that direction with a magnitude of 1.2. Sorry, this is velocities. That shouldn't have a square. 1.2 meters per second in the negative x direction. Okay, so yeah, this can get confusing. For the rolling without slipping, it's not absolute value. It uses those signs. The one that doesn't use that is circular motion. So the circular motion equations depend on absolute values of the angular quantities. So those are the ones that say the magnitude of the velocity is equal to absolute value of angular velocity times r. It looks, they're basically the same equation, but you have to keep straight which one of these things you're doing. Are you doing a circular motion problem, or are you using rolling without slipping to figure out a velocity of the center? The tangential acceleration magnitude is absolute value of alpha times r. And then the centripetal has a square, so you don't really need the absolute value, but it still only depends on the absolute value because the square gets rid of the sign. Rolling without slipping uses signed angular quantities. So those are the ones that say the velocity of the center is negative omega r 0, and the acceleration of the center is negative alpha r 0. Yep.
So I tried doing this problem using circular motion equations, taking a point at the top of the wheel and then dividing that in half because the top was moving twice as fast as the center.
Yep.
But I got 0.6.
I think that's yes, you could do it that way, but I think it's a more confusing way to do it.
Certainly.
So,
I forgot about that.
so yeah, the way to do it is think about, so in any problem that says rolling or suggests rolling, think like, okay, you're going to use these two equations somewhere, okay? Somehow you're going to use the fact that you can calculate the velocity and acceleration of the center of the wheel. And then maybe in addition to that, you have to use relative motion to figure out velocities and accelerations of other points. Okay. So if it says rolling, or it seems like something that you think of as rolling, a car or a bike or whatever, then you're looking for a place to use one or both of those equations. Okay.
Is that little fact about the top being twice as fast as the center, does that apply to velocity and acceleration?
That applies to velocity and the horizontal part of or the x component of the acceleration, not the y component. Okay, so we got the velocity here, and then same thing for the acceleration. And this is the kind of thing, by the way, it's always good. It's a good habit to get into now. It'll serve you well, like in all your engineering classes coming up. Think about the ways that like when you get an answer, think about ways that you can sanity check that answer. You know what I mean? So we know from just thinking about the problem, okay, if the angular velocity of the wheel is this way, it has to be moving that way. If the angular acceleration of the wheel is this way, it has to be accelerating that way. So now you have something that you can check your signs on, you know? So if you got confused about whether, you know, to use an absolute value here or whatever, I guess in this case they'd be the same, but you get an answer. Now you can go back and sanity check that answer with what you already knew about the directions. There's a lot of like redundant bits of information here that you can use to check your steps, you know. Okay, so now the acceleration of the center, which is also the acceleration of the golf cart, the acceleration of the people in the golf cart. So we're going to use the acceleration of the center is negative alpha r 0. And alpha is 12 radians per second squared. But it's clockwise, so negative. So this is equal to negative of negative 12 times 0.15, and then 0 for y. And that is positive 1.8, 0 meters per second squared. And now you already knew from the angular velocity and angular acceleration directions that the thing was slowing down because they had opposite signs. But now you also see that with the acceleration, they have opposite signs, so that agrees this thing is slowing down. Yep. Yeah. Yeah, you'll be given all these equations. That's right. But yeah, some of the subtleties like absolute values and signs and stuff, like you just have to be used to dealing with those. I know it is confusing. I mean, if I had invented physics, I would have made it all equal to 4 pi, you know, but they didn't ask me. It was already here when I got here. Any questions about that one? Any other homework questions? Yeah. Sure. So there's a linkage. And a linkage is just a collection of bodies connected by joints that has enough degrees of freedom to move. If you have a collection of bodies connected by joints that can't move, you apply forces to it and it stays still, like the truss in a bridge or something. That's called a structure. So a linkage, though, is one that moves. So we have this one body that at this instant is positioned like that, and a second body that's positioned like that. And the joint connecting these two bodies is A, and this point up here is P. And we're given that this has a length of 2. And this has a length of 1 meter. And the longer one has a constant clockwise angular velocity. So clockwise is this way, of 5 radians per second. And the shorter one has a constant counterclockwise angular velocity of 10 radians per second. Okay, and we want to figure out the velocity of that point A, the velocity of that point P, the acceleration of A, and the acceleration of P. And this is actually just such a useful thing to be able to do for engineering applications, for machines and stuff, to figure out based on how the individual pieces are moving, what's going on, you know, in an absolute sense of, we'll see that acceleration is the one that's the most useful. Okay, so my first question is, this is not like obvious on its own, but who has a guess? So forget that this is rotating, it says 10 radians per second counterclockwise. Imagine it said it's rotating 5 radians per second clockwise, so the same as this one, okay? There are two possible things that could mean, okay? One is, since it's connected to this body, okay, as this rotates down, this is rotating, this angle is getting more obtuse as it goes. You see what I'm talking about? It's like opening up because it has this 5 radians per second angular velocity from this one and an additional 5 radians per second, okay? How many people think it's that one? Good. Okay. So everyone else thinks it's the next one. That's correct. I'm telling you right now. That's what it seems like. Okay. Seems like everyone knows what this answer is going to be. So the other possibility, that was supposed to be funny, but I didn't. So the other possibility is that as this thing rotates, this thing has the same angular velocity relative to the ground, and that means that this would stay exactly at 90 degrees as this thing rotates down. Who thinks that's the case? Nobody? That's how it is. Okay. So the angular velocity and angular acceleration that's given, no matter what body you're talking about, what it's connected to, those are measured relative to the ground. Okay? There's such a thing as like an absolute angular velocity and an absolute angular acceleration, and that's what's always given. Okay? So if it said this had 0 angular velocity and this one had 5 radians per second, this one would rotate down and this one would just stay, it would do that. Okay, this one would stay in the same orientation the whole time. Okay. So in order to come up with the velocity of that point A, we have to visualize what's going on. And what's going on is that point that's part of this horizontal bar, right, it's connected to it, is just moving in a circular path around this. And it doesn't have to complete the whole circular path. It's just at this instant, we know that it's moving in a circular path around this center of the circle. Okay, so okay. And so now it's a pretty straightforward problem. We're talking about a circle with a radius of 2 meters and an angular velocity of -5 radians per second. So let me draw that out. So here's our circle. here's the center. This is just to visualize what's going on. This is the point A. It's rotating clockwise at 5 radians per second. And now we can go through our steps for figuring out the directions of these things. What's the direction of the velocity vector of that point A? Yeah, negative y direction downward. So that's the velocity. Is there any tangential acceleration? Or how do we know? Yeah, there's no angular acceleration. It's a constant angular velocity. So there's no tangential acceleration. And then centripetal is always the same. If it has velocity, it has centripetal acceleration. So that's this way. So the magnitude of the velocity, the speed, is equal to the absolute value of the angular velocity times r. So that's 5 times 2, so 10 meters per second. And we already figured out the direction. So the velocity vector is 0, negative 10. Or 10 meters per second down. Let's do the centripetal. Let's get the acceleration while we're here, even though it doesn't ask for that until part C. So the centripetal acceleration magnitude is omega squared r. So that's 5 squared times 2. So 50 meters per second squared. So the centripetal acceleration vector is in the negative x direction. We figured that out at first. So this is negative 50, 0. And that means that the total acceleration of A is negative 50, 0, plus the tangential acceleration, which was 0. So negative 50, 0. Okay, so now let's figure out the velocity and acceleration of the point P. Okay, so while this point A is doing its thing, that point P is moving in a circular motion around A. Okay, so we're going to have to use relative motion. So for part B, the velocity of P relative to the ground is equal to the velocity of P relative to A plus the velocity of A relative to the ground. This one we got from part A. And the velocity of P relative to A is a circular motion question. Okay, so now let's imagine that that point A isn't moving and figure out what the velocity and acceleration of P are relative to that point A. That now, for a second, we're going to assume that it's fixed. So for the velocity of P relative to A, we can think of this as a circular motion again. The center of the circular motion is A. We're given that there's an angular velocity of 10 radians per second counterclockwise. This is the point we care about now. So the velocity vector is to the left. Is there any tangential acceleration? I'm just going to move. Right, there's not, because it's a constant angular velocity. Okay, so what we're doing now is calculating the velocity of P relative to A. There is a centripetal acceleration, and that's this way. The magnitude of the velocity is the absolute value of angular velocity times r. So that's 10 times 2. One, yeah, you're right, sorry. So yeah, the radius this time is 1 meter. That's in the negative x direction, so the velocity of P relative to A is negative 10, 0 meters per second. And so now we can put these together. The velocity of P relative to the ground is equal to the velocity of P relative to A plus the velocity of A relative to the ground. Now we have both of these, so it's negative 10, 0, plus what we got in part A, 0, negative 10. So this vector is negative 10, negative 10 meters per second. So it's moving with, so, okay, so look at that vectors. That has a magnitude of square root of 200, and it's in the third quadrant at 45 degrees. So look back at this picture and see if that makes sense. You know, this thing's rotating this way, this thing's rotating that way. The net result of that is that at this point right now is going 45 degrees that way. Any questions about that step? Nope. It's that angle's getting more acute because so this one's rotating down, and as it does that, this one's rotating, like closing like a jackknife. I don't think there's any reason to do it differently, but you're always welcome to. There's never a problem where if you want to choose a different one, it wouldn't be allowed, you know. but I don't think there's any benefit to changing it in these. In the rolling without slipping problems, there is. Any other questions? All right, so it's sort of the same process for the acceleration. So for part D, part C is figuring out the acceleration of A. We already did that. So now we're figuring out, well, we're going to use the relative motion equation that says the acceleration of P relative to the ground is equal to the acceleration of P relative to A plus the acceleration of A relative to the ground. We already have this. And this one is circular motion of that point P around A again. So now we have to think about the acceleration of P relative to A. I guess I'm going to draw that picture again. It's the same picture that I just had. So here's the point A, that's at the center. Here's that bar. It's rotating this way. At 10 radians per second with no angular acceleration. So the velocity is that way. We already know that. The centripetal acceleration is this way. We already figured that out too. The magnitude of the centripetal acceleration is omega squared r. So that's 10 squared times 1. So that's 100 meters per second squared. It's in the negative y direction, so the centripetal acceleration is 0, negative 100. There's no tangential acceleration. So the acceleration of P relative to A is 0, negative 100, plus the tangential acceleration, which is 0. So you just get 0, negative 100. Yes?
How do you know it's negative 100? How do you turn it into negative?
Because when I first drew this picture of the circular motion, the centripetal acceleration is always toward the center from whatever point you care about. So toward the center is down, and that's our negative y direction. Okay, so we have that. Now we can add these together. So the acceleration of P relative to the ground is equal to the acceleration of P relative to A plus the acceleration of A relative to the ground that we got way up here, negative 50, 0. So the acceleration of that point P is negative 50, negative 100. Any questions about that one? Any other ones of these you'd like to see? We can just finish today with this stuff and then go on to new stuff tomorrow. Anything? Okay. Okay. So particle kinematics, number 16. You have a passenger on an airplane. The airplane has an acceleration. Okay, so here's the airplane. And its acceleration vector the acceleration of the airplane relative to the ground is negative 3.5, 7.0 negative meters per second squared. So the way I have this drawn, that would mean it was slowing down. The passenger drops an object, so what would the acceleration appear to be to an object, to an observer on the plane? So you can think of the observer as being like a camera that's watching this, measuring how it moves. We know that the acceleration of the object relative to the ground, it's in free fall. So this is just going to be 0, negative 9.81.
Would the x component not be affected by the acceleration of the airplane?
It's not. That's right. I mean, there's nothing. So okay. So here's all you have to think about. So the object, is it touching anything? No. And then the other question is it moving fast enough compared to the air around it for there to be a significant air effect? There's not, because it was just dropped in air that's moving the same speed as it. So yeah, it's in free fall.
How's that different from an object being dropped from a area has like an initial velocity?
Yes, it does have, and maybe my drawing is a little misleading here, but everything we're talking about here is accelerations. But it does have a velocity. If somebody were happened to be like hovering in the air and could videotape this object from their viewpoint, it would look like this object was a projectile motion with an initial velocity of 500 miles an hour or whatever, you know? It's actually moving really fast with the plane. But that's velocity, not acceleration. And velocity doesn't affect the acceleration of something in free fall or projectile motion. Right. I mean, it would be moving in a parabola, like some kind of shallow parabola, just like any projectile motion. Okay, so and then we'll put this together. So acceleration of the object relative to the ground is equal to acceleration of the object relative to the airplane plus the acceleration of the airplane relative to the ground. Do the algebra. We're trying to figure out the acceleration of the object relative to the airplane. And that's equal to 0, negative 9.81. subtract the acceleration of the airplane relative to the ground from both sides. And so you get minus negative 3.5, negative 7.0. Just doing the algebra. And so you get that the acceleration of the object relative to the airplane is positive 3.5, negative 2.81. So to a passenger on the airplane, if that passenger didn't know that they were accelerating, it would look like this thing was falling really weird, okay? Or even you could think of this as a way of recognizing that you're accelerating. If you drop something and it's in free fall and it accelerates really weird like this, you know that your vantage point is accelerating. Okay, it looks like it's accelerating in the positive x direction and accelerating very little in the negative y direction compared to what you're used to. Any other homework questions? Okay. Well, let's stop there. So tomorrow I'm going to just get right into it with the new material. And then Thursday we should have some time for questions. Yeah. Sure. On the same particle kinetics. Okay, so this is similar to problems that we've done a lot of. It's just that you have to do everything in terms of constants. So an object's launched into the air from a height of h and at an angle. Okay, so here's the ground. And the object is launched this way, where this angle is theta, and the initial speed is capital V. And we want to calculate the greatest height. And how long it takes to hit the ground. I'm going to put my coordinate system, like I always do, on the ground right underneath the object at the instant it's launched or starts its flight. And my time equals 0. So for part A, time equals 0 is going to be when it's released. Time t is going to be when it reaches the highest point. And now I can start to fill out what I know and what I want. So time t, acceleration, initial position, position at time t, initial velocity, and velocity at time t. We don't know t. We know that the acceleration is 0, and it says instead of using negative 9.81 meters per second squared, to use negative g, you know. So this is going to be 0, negative g. At time 0, the position is 0x positive h for y. For the position at time t, we don't know the x position. we're trying to find the y position. So this is what we're looking for. And the initial velocity, to get that, we know that it has a speed, capital V, and it's at this angle, theta. So that initial velocity vector is going to be V cosine theta, V sine theta. So that's this one. And what we know about the velocity at time t when the object's at its highest point is that the y component is 0. And so I think we can use the y equation that says 2ay times the quantity p minus p0 y is equal to vy squared minus v0 y squared. So we have negative 2g times the quantity py minus h is equal to 0 squared minus v sine theta squared. So negative 2g py plus 2gh is equal to negative v squared sine squared theta. We're trying to solve for py, so negative 2g py is equal to negative v squared sine squared theta minus 2gh. And if you divide everything by negative 2g, you get that py is equal to, there's a few ways you could simplify it, but I'll leave it like v squared sine squared theta plus 2gh. I guess I'll take this, now I'll leave it in there. Divide the whole thing by 2g. And then for the time it takes to hit the ground, I guess I don't have time to do this, but you have to choose a new, so time equals 0 can still be the instant that it's launched. The time t, though, now has to be when it hits the ground. So you're going to have to go back through that list and adjust some of the things that you know. But you can solve it with that same kind of approach. Okay, that's all.